Very much. Really excited to be here after 6 years. So I basically do research and teaching. I work broadly in fluid mechanics, and I do somewhat unconventional fluid mechanics. We use particles to simulate fluid flows. So my PhD work involved this thingy here, which uses vortex particles to, keep track of the fluid flow. Also teach in an aerospace engineering department that explains this airplane sitting there. But in my copious spare time, I've also been working on Mayavi. I built the original Mayavi and built the second version as well. Just to note, Mayavi is not dead, it's still alive. It works on Python 3. I will be sprinting on it, so if you're interested, please join me. I took a 2-year break from academia to help set up Nthought India, but I'm back in academia now, and I continue to teach at IIT Bombay, and I consult for Nthought. Okay, so this talk is about PySPH, which is a framework that we've been working on for several years now. In fact, maybe 2010 or so, I think I even had a presentation here about an old version of PySPH. And the work is based on the work of students, as always. So Kunal Puri is a PhD student of mine, and he wrote a lot of code for PySPH. Chandra Kaushik actually worked on an initial version, which I presented earlier, but the current version is largely, I rewrote most of the code. So Pankaj is another of my students who worked on some of the solid mechanics stuff, and so I'd like to thank them. There's some other new contributors. There's a third-year undergrad student called Aditya who's been sending some pull requests on PySPH. Another senior student on Anshuman. They added a few features recently. And some other students have made some small improvements, but bulk of the development has mostly been kind of my weekend project. All right, so the outline of this talk is an introduction, super fast introduction to SPH. I'll try to keep it short without too much math. I do have some math, but it's not too much. And then go over the issues. What are the problems? Why is it that we're trying to build this? And then talk to you about PySPH itself. So the goal is to be able to simulate complex fluid flows, but not necessarily restricted to fluids, but that's my personal goal. This is difficult because the equations are nonlinear, partial differential equations are nonlinear. You have difficult boundary conditions, and what I'm trying to look at is moving boundaries, free surfaces, and a general purpose tool to handle these, which is not necessarily the strength of tools like finite volume or finite element schemes. So this kind of falls in outside of that domain. So here's a typical example. I hope it works. So there's basically water that was stacked up. It doesn't loop for some strange reason. So basically, when you start off, I'll just pause it. There's basically a dam of water here, which is released. And then there's this floating SPH. I just cooked it up with something. I think I used Gmesh to generate that. It's represented as a bunch of particles. The water hits it, and it's not physically realistic, but it looks pretty. So the idea is you can do simulations like this with PySPH. So we want to be able to solve problems like these. So the idea is to handle the nonlinearity, at least the difficult part of the nonlinearity, we use a Lagrangian technique like SPH where the particles move, right? So you don't have to discretize the advective terms. And the boundary conditions are still hard, but they're a bit easier in this case because especially for the free surfaces, you don't have to do anything special. The particle moves to where it should be, and that captures the surface. Moving bodies, again, straightforward because it's a Lagrangian technique. And it's general purpose because the framework allows you to pretty much discretize almost any PDE. FEM people will probably show me a big red flag saying, no, it's not higher order, it's not accurate, blah, blah, blah. But yeah, but it's general purpose in the sense that you can do a fair bit of good PDEs with it. So my personal interest is I'm interested in building mesh-free tools for general purpose usage. And I want something to be accurate as the method's supposed to give you. And I want it to be easy to use, extensible, and reproducible. So SPH has its history, 1977. 2 independent researchers worked on it. But then Monahan, is kind of like the big daddy of this scheme. He's published a huge amount of literature on SPH schemes. Basically, they let you do PDEs, complex problems, moving geometries, free surfaces, do multi-phase flows. All of these are possible within the SPH framework. So how does it work? Well, it basically starts off with approximating an exact integral with an approximation that looks like this. So if you replace this W with the Dirac delta distribution, this will be an exact expression, but instead you replace W with something called a kernel, which has compact support, and such that as this h, which is a size parameter of that kernel, as it goes to 0, it tends towards a Dirac distribution. So it's an approximation of this identity, and you use this to represent a field property. So you have these bunch of particles. Each particle has this field representation, and together they give you the ensemble of all of those gives you the field property. So if you have a particle at some location A, you can find the function value by simply discretizing that integral into a summation, like so. And because the kernel W is compact, you only need to look at your nearest neighbors. So you sum over only the nearest neighbors of this particle A. So NA is a set of neighbors of particle A. And then you need to estimate the volume that you associate with each particle. And that's typically done in SPH by using m by rho. So you associate a mass with each particle, you have a density, and then you sort of approximate. So this is one of the reasons why some people say, it's ad hoc and all of this. But there are better ways to do this. This is just like a SPH 101. Now the nice thing is, if you want to take a derivative, you take the derivative and you transfer it to the kernel, which means you can very easily calculate derivatives because your kernel is a nice differentiable function. But this has problems of its own, and people have consistently found that there are better ways to do this because you have no sense of organization with the particles. The particles are all over the place. So you're not going to get very good accuracy unless you do something special with how you do the derivative. So there are a whole bunch of schemes and techniques that you can use to get much better representations of derivatives. For example, this is one common trick. You add and subtract 1 or the gradient of 1, which is 0, such that you make sure that a constant is recaptured, things like that. But the idea is very simple. You take the derivative of the kernel, and you have some kind of expression like this, which discretizes your derivative terms. So now if you take, say, an example like a continuity equation with conservation, a representation of continuity of conservation of mass, you have something like d rho by dt. Rho is the density. You have minus rho divergence of the velocity field. And that in SPH form becomes this. Over each particle A, you have an ordinary differential equation, which the right-hand side is just a summation over neighboring particles. Right? So the idea is if you have a collection of particles that discretize a field, a fluid field that you're interested in, you given a particular particle, you identify its neighbors, and then you find out the interactions of a neighbor on this particular particle. Right? And that gives you the right-hand side of your ordinary differential equation like this. And then you can integrate the ODE with any standard technique. That's the big picture. So it's Lagrangian, derivatives are transferred to the kernel, and you convert a PDE to an ODE. Okay. So you can do this for the free surface problem. I'm going to skip this because you already saw it. Here's a bigger example. A student of mine did this. Same thing, different geometry. But it's easy, trivially easy to create these things. That's a fluid rigid body coupling. And this is something different. This is basically you have two steel rings that are going to collide, and you're going to see how they collide. So you can do elastic dynamics as well, not just fluid mechanics. You can do this as well. So it's kind of nice because it's attractive for me because here's a general purpose tool that I can make available, and different people can apply it to a variety of problems. Okay, so the good is that it's fairly easy to write an SPH code. And this is the downside of SPH as well, right? If it's easy to write, everybody rolls up their sleeves and has their own implementation of it. It's very general purpose. It's widely applied, and it's very easy to parallelize as well. Okay? It lends itself to all of that. The bad is, because it's easy, there's a cottage industry for schemes. Everybody, you and I can sit together and come up with a new scheme tomorrow and publish it. It's a bit ad hoc, and FEM guys have very rightfully to say that. So it looks very ad hoc in that sense, the way in which you do the discretization. There are much nicer ways to do it and describe it, which sort of doesn't have the same kind of rigor that you would have with a grid-based or a FEM scheme. But that's something I'm not interested in fixing right now. I want to build a tool set. The particle disorganization is another issue, which again is not necessarily related to the tooling, but you can have algorithms that fix that. In general, it's slower than grid-based schemes for fixed grid problems. If you have an equivalent problem, you can solve it with a fixed grid, go with it. The other big issue is it's hard to reproduce results. But this is, again, not specific to SPH. It's common to many numerical methods. And that's just the nature of publication industry today. So we want ease of use for research. These kind of problems are intensive, so you require HPC. You want it to be parallel. You want it to use distributed as well as multi-core, and you want reproducibility. So ease of use. So let's get a little more into it. Can I have an undergrad student, not a postgraduate student, because I don't get most of the undergrads from IIT come here to do their PhD. So I don't necessarily get all the good undergrads to do my PhD. I have undergrad students. So can I have an undergrad student use and extend these tools? Can they actually do a reasonable simulation? Can they actually reproduce a paper with the tools I built? So to do this, well, we make it open source, of course. It's cross-platform. We want to worry about ease of installation. And we want performance, because it's an undergrad student who doesn't have the huge amount of time you could write something high performance. And here is where language really matters. If I throw a C++ code to a student, I'm not going to get any work done. And I've tried this for tens of years. It does not work. On the other hand, if it's Python, they're very quick. You can look at an example, change it, modify it, and get running very quickly. This one's easy. Can you ensure that the code is functioning correctly on platforms? We all know how to do this. I'm not going to belabor this at all. But the reproducibility issue is a lot more involved. Given a paper scheme, can one reproduce all the results without the author, right? Or without even being the lab of the author? And that's much harder. I'm not going to bore you with this. I'm going to skip this and move on. But we all know that reproducibility is important, and that even in CSE, there's been this awesome study at Arizona which suggested that only 217 of 601 CSE papers could be built, let alone be reproduced. And it gets worse in other fields. So it's pretty pathetic. And I take a bet. If you pick a good journal, pick a good paper, it's very unlikely you'll find the source code for it. The probability is very, very small that you'll actually be able to reproduce every single computation. It's very rare to find that. So we want to see if we can help with this at least. So I introduced PySPH. The idea is we want to provide common infrastructure needed for particle methods. Now this is very ambitious, I know. And I know there are people in the audience who do particle methods, and there's stuff we don't have to support them yet. But the goal is to get there. It's on Bitbucket. Come back to that in a bit. So language choice. So I started off, I think in 2009, writing a little C++ implementation because I was used to C++. I used to Swig. I've used a bunch of stuff. The problem with this tool chain is that you use C++, you use Swig, and then Python. You now have, instead of one problem, you have three problems. Right? You have C++, and then you have Swig, and then you have Python, and you have all the binding issues that you need to worry about. Are you sharing the same memory? How do you pass things around? All of that stuff. And then in 2009, I did a study. There was even a blog post, one of the rare blog posts I made. I did a study of, okay, C, C++ versus D versus Python versus blah, blah, blah. And I found that, okay, Python's awesome. So you switched to saying, let's use Python for everything. The problem with Python was the abstraction of using, that's not abstraction. The fact that you're using Python leaks right through to the user. So the undergrad student actually has to know Python. And now he or she has to write their extensions also in Python, which means now they probably have to build a setup.py, build the thing, ship it. So it's just not very extensible. So, and the other issue is debugging Python is not that straightforward. As in, if it's C++, you know exactly what to do. You can build an executable, run it with GDB, step through. But if it's a mixed language beast, it's much harder. Then in 2013, it struck me, wait a minute, why am I doing all this? Throw that all out. Let's just do everything in pure Python and generate the rest of the code. Right? Everybody seems to be doing that these days. So the goal was to make the user side pure Python. So what it does is you have a user layer that's pure Python. We auto-generate HPC code. We support OpenMP on the fly. It also works with MPI, so you can do MPI run on the same Python script you run, and it will run on multiple machines. Performance, of course, depends on a bunch of things. And we use Zoltan to do the distribution of the particles. It's cross-platform, so it works on, everything. The current focus is on SPH, weakly compressible transport velocity, elastic dynamics, and compressible SPH. All right. So it's on Bitbucket, and I'm probably going to move to GitHub simply because I can't do continuous integration that well with it's just incredibly frustrating. So I'm going to move installable via pip. We use unit tests, skipping that. So how do you get started? I just pushed a release early this morning, 1.05 alpha 5. pip install PySPH should work. It just depends on Python, and you need to have a working C++ compiler on your machine. So I want to do a quick demo, but I think I have just 5 minutes, so maybe I'll just do it. So let's say we run a simple example. Okay, so this is just a cube of water, so it's boring. But if I just run it, what it does is it's it's just going to run the code. It's going to compile in this case, it was pre-compiled. I just ran it before I came here, and it took about 7.82 seconds. The nice thing I can do is I can say, and it'll run the same thing, and it's actually like 4x faster. It's a 4-core machine. So I don't have to do anything. It's pure Python. And it kind of does all of this by magic. Oops. I'm just going to run this so I can come back to it. So the other thing I didn't demonstrate is that it actually has a built-in viewer for the data. So you can just run, after you run a simulation, you can just say PySPH view the data directory, and it'll kind of view the directory. You can pass a whole bunch of command line options. So you do any of these, you just run -h. There's a built-in set of command line options you have, so you can script this on the command line as well. You can do the OpenMP that I showed you. So the idea is the user writes serial code in Python. PySPH generates the high-performance code, and the same exact code is used for parallel and serial stuff. So the way it works is you create a bunch of particles, you choose a scheme, and you run the simulation. If you want to create a scheme, basically the scheme specifies a bunch of these equations, and you specify the integrator. So here's a quick example. So you do a bunch of imports. I'm going to skip this. And then you can write little application saying this is a Taylor-Green problem, which I have a complete example that's checked in. You can add a bunch of user options in addition to what PySPH already provides. You can consume those. So after it parses the command line options, it will call this back. You create whatever particles, and then you can create a scheme, configure the scheme, and then do any post-processing. So this is a typical example, and we ship with 35 examples. So if you do pip install PySPH, you actually get 35 runnable examples. So I'll just quickly show you that. So if I do PySPH -h, you see that it gives you like view, run, dump VTK, and test. So you can run a test suite. Let's see, view. That's the elliptical drops, and it'll pop up a little Mayavi-based viewer, which allows me to quickly look at the visualizations. And I can change the particle properties, do all the nice visualization that I wanted to do. You can also dump these files if you don't have VTK installed. You can dump them to VTK files and view them on a different machine. And if I do PySPH run, it'll pick out all the installed examples that are built, and there are 35 of them. You can basically pick one of these and just run them. And these are all importable as well. So you can basically say, okay, I want to take the implementation that I have and subclass. So if you want to just change the scheme, you just subclass it, change the scheme out, and you can implement your own scheme, and you get all the post-processing, everything is taken care of for you. So it's really nice to do reproducible research. So here's a typical example. That's the equation, and that's what you'll write in Python. So it's kind of, if you look at this and look at this, it looks kind of straightforward. It's a bit messy, but it's pure Python. So it's very easy for someone to look at a paper and write out the expression of what you want to do. I'm going to skip this. And the idea is, from the example, we have a Mako template for all SPH simulations. That template yanks in all of the user code that's been given, generates Python carefully, and compiled. So I'm run out of time, so I'm going to skip all the way to the end. Just want to highlight that we have 35 examples that are completely reusable. So I kind of wrote a paper using this approach. So I have one script which runs all my simulations, generates all the results, so that with one command, I can basically run automate. It'll generate all my images in a directory, and then I just run PDF LaTeX, and I have my manuscript. You can check out the paper. I'll leave my slides somewhere so you can grab it. So it's a very small community. I'm really happy if people can join, use it, and send pull requests as well. Hopefully, I'll get to using Loopy soon, get really good performance. So in summary, it's a pure Python front end. It's fast. It supports OpenMP and MPI. It ships with a bunch of examples, and it has good support for automation of pretty much everything you do. In fact, I spent a lot of time trying to design it to facilitate reproducible computing. Sorry, I ran out of time.
Thank you. So we have about 5 minutes for questions. Go ahead.
Thank you. Is the particle placement random? And if it is, do you have a random number generator? And if that's true, does that present a challenge for reproducibility?
So the question was, okay, I don't think I have to repeat the question, so okay.
Go ahead.
So the way it starts is when you start your initial discretization, you start with an initial condition, and that is user specified. So if the user chooses to use it completely randomly initialized, then it's a problem. But what I tend to do, sometimes you want to give a random distribution so you don't have a preference for one particular direction. What I tend to do is I set a seed so that all simulations start with the same set of random numbers. So that gives me reproducibility whenever I need to do that. But otherwise, it's in the user's hands. So PySPH doesn't really say anything at this point. As in, you give an initial condition, it's just going to do an integration over that. That's it.
Not when the random number generator comes in.
So that's done at the initial time when you're creating your
But
particles.
you also call a random number generator.
No, I don't. Because
don't?
all I do is I integrate those ordinary differential equations. There's no randomness in that. So if you have a forcing function, for example, which is somehow called within your main iteration loop, then you would have this problem. And that is dependent, say, on the number of particles or whatever. Yes, then that's a problem. But
can you tell us a little bit in more detail about boundary conditions and how you do those?
okay, so SPH again, there's a whole slew of techniques for this. The one that I find that works pretty well is there's a paper by Adami and Hu. So this is in the context of incompressible fluid flows. So what they do is, so let's say you have water in a tank. So you have your boundaries. So what you do is you discretize your boundaries into, say, an array of 3 or 4 particles, just so that so the thing I didn't tell you about is when you take the derivatives of the kernel, on the kernel, you're essentially having another term that you're dropping off because you're relying on compactness of support. So what you do is, if you have a boundary, you have a wall, you discretize that into another set of particles. You kind of interpolate the fluid properties onto that such that you get a continuous distribution, and then you do it. And that seems to work pretty well. So there are a bunch of techniques, and this is one of the techniques. So the idea is, this is just a framework, right? So we have the transport velocity formulation implemented, so you can play with that if you want, but you can implement your own, because essentially all you're saying is, in a boundary condition, you have some boundary particles, you have some, say, fluid particles, you have some set of properties. So if the user wants to say, all right, interpolate these and put them onto those, you can write out a little equation that says that, and it put it into the framework, and it'll do it for you. It's just another interaction between 2 sets of particles. So that's kind of what you do.
Thank you. Let's thank the speaker again.